Here's a simple circuit. It has a cell with an EMF epsilon and a resistor is connected. Current flows out and through the resistor, and you can see from the picture that 4 amps is the amount flowing through. But what if you wanted to measure the 4 amps? You would use something called an ammeter. You cut the wire, you place the ammeter in series, and then you let the current flow. As you can see, the 4 amps passes through the ammeter, and so it registers the amount of current passing through the resistor. But this trick only works if the ammeter has 0 resistance. After all, what would happen if the ammeter had 5 ohms of resistance? By connecting this ammeter, you've added resistance to the circuit, and so less current comes out. And now the ammeter reads 3 amps, which is not the true value. That's too low. So this is why an ideal ammeter has 0 resistance. Now let's figure out how to measure voltage or potential difference. We're going to add another resistor, and for simplicity we'll say they both have 2 ohms. The cell, we're going to make 30 volts of EMF. Just like before, current flows out, it passes through this first resistor, and the voltage drop is 15 volts. That's the potential difference across the resistor. And then the current continues, and there's another 15 volt potential difference across this resistor. Why do the 2 resistors share the EMF equally? Why do they each consume half of the EMF? The reason is because they have equal resistance. Now we know that there's 15 volts of potential difference across the resistor because we saw the current passing through. To actually measure that, we use something called a voltmeter, and we connect it in parallel across the resistor. Now you want this voltmeter to have infinite resistance so that when current flows, it doesn't get diverted away, it continues along the same path as before. If you have some non-infinite resistance, like 2 ohms let's say, then when current flows through the wire, you have 20 volts now being dropped across the first resistor, and then when current reaches this junction, it splits, and you only have 10 volts of potential difference across the second resistor. By splitting the current, you've reduced the potential difference. Why is it half of this potential difference? The reason is because you have 2 parallel resistors, each with 2 ohms, and so their total is 1 ohm of resistance. And so the effective resistance is half of this guy's resistance, which means that this potential difference is half of this one, but they still have to add to the total of 30. So that's why this voltmeter has to have infinite resistance, so that you don't divert away any current and change the original circuit. So what have we learned? We've learned that when you want to measure current, you use an ammeter. The ammeter is connected in series with the resistor, and it has 0 resistance in an ideal world. If you want to measure potential difference, you use a voltmeter. The voltmeter is connected in parallel with the resistor, and in an ideal world, it has infinite resistance. In IB questions, you'll probably encounter some problems where things are not ideal. Take this question from a past IB exam. They've connected a voltmeter, and it's correctly connected in parallel with the resistor. So what's wrong then? Take a moment to inspect the resistances. The voltmeter and the resistor have equal resistance, and that's not right. The voltmeter should have a giant resistance by comparison to the rest of the circuit. Why is this scenario wrong? Well, you're changing the potential difference that you're trying to measure. When current flows out, it reaches this junction, and now some can flow through this pathway, which doesn't have infinite resistance. By opening up this second pathway, you've made it easier for current to flow through the bottom half of the circuit. That means the bottom half of the circuit has a lower resistance than it did before connecting the voltmeter. And when you lower the resistance of the bottom half, you lower the portion of EMF it consumes. And that's why you change the potential difference when you connect this voltmeter. So if you connect the voltmeter and the resistance is too low, you change the voltage that you're trying to measure. Here's another common non-ideal scenario IB questions like to present. Instead of connecting a voltmeter in parallel, they connect the ammeter in parallel. And instead of connecting the ammeter in series, they put the voltmeter in series. And they ask, what's the reading on the ammeter and what's the reading on the voltmeter when you do it wrong this way? To answer the question and figure out what the meters show, consider their resistances. The ammeter has 0 resistance. The voltmeter has infinite resistance. So when current flows out from the cell, it's going to bypass the 6 ohms and it's going to go straight through this way, taking the path of least resistance. It's almost as though the 6 ohms isn't there and this is just another wire. Okay, but what about this? This has a huge resistance, so when current passes through, it's going to be blocked by this giant resistance. In fact, if the resistance is infinite, then no current will be able to flow through the voltmeter. Therefore, no current can flow out of the cell in the first place. So if no current flows out of the cell, then there's no current flowing through the ammeter, and the reading is 0. Now let's figure out what's happening with the voltmeter. First, we have to see that this circuit has 3 things in series. There's this sub-circuit with the 2 parallel branches. That sub-circuit is in series with the 6 ohms, which is in series with the voltmeter. Whenever you have 3 things in series, they share the 6 volts of EMF, and they share it based on how much resistance they contribute to the circuit. So, of the 3, which one gets most of the EMF? Clearly, it's the voltmeter because it contributes most of the circuit's resistance. In fact, these two pale in comparison, and they effectively don't contribute any resistance at all, and therefore they don't get any of the EMF. By contrast, the voltmeter contributes all of the resistance effectively, and therefore it takes up all 6 volts of the EMF. And that's the reading it shows. It reads off the 6 volts that it dissipates.